All right, I am excited for today because the study that we cover today is one of my favorite studies of all time. It's another study by Bobbert and Van Soest, the same authors of the review article that we read to start off this subtopic on jumping here in class. Paper's titled Effects of Muscle Strengthening on Vertical Jump Height, a Simulation Study. I like this study primarily for two reasons. One, it uses computer modeling and simulation, which is one of my favorite approaches for doing biomechanics research. And two, when you do computer modeling and simulation studies, it can often, not always, but it can often be difficult to produce results that have a real clear, compelling, practical take-home message in terms of what can I do with these results to, for example, help improve athletic performance or help improve human health. Not that you can never do that, or that it's necessarily difficult to do that in a simulation study versus a typical study with experiments on live human subjects. But it can sometimes be challenging to have that real clear, practical take-home message in a simulation study. This study is a great example of a computer simulation study that does have a real clear, compelling, and practical take-home message for the purposes of training to maximize vertical jumping height. Now, what were they doing here exactly? They created a computer model of human jumping for maximum height. And what is that model? Well, this is their model here. It's got four body segments. It's got a trunk that I'm highlighting with my mouse there, and then a thigh and a shank and a foot. Okay, so four body segments, three joints. It's got a hip joint, a knee joint, and an ankle joint. And you can see the model also has these kind of springy box-looking things on it. What are those exactly? These things labeled glue and vas and gas. What's that exactly? These are models of muscles, or models of muscle groups specifically, attached to the model that spans its joints here and is representing the mechanics of muscles. Each one of these muscle-looking things here receives what they call in the paper a stimulation signal, and what you'll hear me often refer to as an excitation signal, which is this control signal from a hypothetical nervous system that is input to the muscle and causes it to produce force. So kind of the way the model works here is that it's got these joints, and these joints are actuated or controlled by these muscles that surround the joints. Each one of the muscles receives from the model's nervous system a excitation signal that causes it to produce force. Those forces, based on the moment arms of these muscles, their distances from the hip and the knee and the ankle, end up producing moments about those joints that rotate the model's joints and cause it to move and cause it to generate ground reaction forces and perform movements like a vertical jump here. It looks like the model has just one leg. For all intents and purposes, it has two legs. They doubled the mass of the thigh and the shank and the foot here so that it represented twice the mass of a typical thigh, shank, and foot. So that's representing both legs. And then doubled the strength of the muscle models to represent both the muscles on the left leg and on the right leg. So really what's being assumed here is not that the model has one leg, but it's being assumed that it has two legs and that it acts symmetrically, that the muscles on the left and right are the same, the joints on the left and right are the same, and they move symmetrically. When the left hip is flexing, the right hip is also flexing, for example. So really it's got two legs. It just assumes that the legs are symmetric and are always moving symmetrically, which is typically what you see, at least close to perfect symmetry in a good vertical jump. Not exactly perfect symmetry, because bodies aren't perfectly symmetric, but that's what's being assumed here, and isn't a huge departure from reality much of the time. So how does this model work exactly? What does this look like? What is it exactly? Here I have a simplified version of this same model for vertical jumping. This is an example of a model that I use and that I teach students to create in my 700 level graduate class when the students in the lab for graduate programs learn about computer modeling and simulation and learn how to create and use these models. And this is what that model looks like. It's simpler than the model in the paper for today, but is conceptually similar. So here it is performing a vertical jump. So this model here is lacking a foot. I took that away to simplify things, but it's got a trunk and a thigh and a shank, so it's got a hip and a knee. And it's only got two muscles here. You can't see them here, but it's got a glute muscle that extends the hip and a vasti muscle that extends the knee. So just two muscles controlling the two joints of this simplified model. So what does it do in here? If I run that again, you'll see it starts in an initial static squat and then starts extending its joints and jumps into the air there. Okay. What the user does is you specify the initial pose of the model down here with these Q values, and that specifies the specific pose of the initial squat, how much the trunk is flexed and how much the hip is flexed and how much the knee is flexed, etc. The model then automatically computes the necessary excitation levels of the muscles that produce the necessary forces that hold the model in that static squat indefinitely. Okay? What the user does is you then would fiddle with the values of these two blue variables here called upars1 and upars2. What are those? You can see here that I set the duration of the simulation to half a second, which is roughly the time it takes to do a decent vertical jump. What's being set in these two blue variables then is the bang-on times of the muscles. And what is that exactly? Those are the times. So when I say 0.1 here, what is that? 0.2 here, what is that? Those are the times within this 0.5 seconds that these respective muscles, for the first one here, the glute muscle spanning the hip, and for the second one, the vasti muscle spanning the knee, those are the times within those 0.5 seconds that those particular muscles would switch from their initial static squat excitation up to their maximum possible excitation of 100%. Okay, so the time within this 0.5 seconds that those muscles bang on, that they switch from doing a static squat excitation to doing maximum excitation and trying to jump as high as possible. What the model actually looks like in practice, like when you actually create this model, what does it look like? This is, for all intents and purposes, the model. It's a series of equations, specifically differential equations, that are basically an elaborate version of F equals ma, right? Ma here would be like the mass and inertial, M here would be the mass and inertial characteristics of the segments of the model. A here would be the acceleration of the model, its motion, broadly speaking. And F here would be the forces applied to the model, the forces from the muscles, the forces from ground contact, forces from gravity, all the forces applied to the model. Knowing those forces, which I could compute from, say, the excitation signals of the muscles, and knowing the masses, which come from my definition of the model, I could compute the accelerations of the model, and then I could integrate those accelerations to get the velocity and positions of the model. I would then repeat that process over the whole 0.5 seconds and eventually solve for the entire time series of movement of the model over those 0.5 seconds. Okay? So what the user does here and what they're tasked with doing for the homework for this model in the graduate class is you're supposed to adjust these bang-on times, and if you want to get real complicated, also adjust these initial kinematic variables here that define the initial flexed pose of the model, the initial pose of the squat jump, to get the model to jump as high as possible, to maximize the peak height that the model's center of mass gets to here when it's performing the jump. Okay? So you could just do that manually, right? And that's what I have them do in the graduate class. Just manually change these values, like maybe instead of 0.1, you make this one 0.14 seconds and this one 0.22 seconds or something like that. Run it again and just run it repeatedly, and then figure out what specific values of these bang-on times and of these initial postural variables cause the model to jump as high as possible. Okay? With these four variables, that would probably take you a while to do that, right? To systematically change them and figure out what combination makes the model jump as high as possible. That would be even more difficult and time consuming with this model here, which has 6 muscles and 3 joints, rather than my simplified model there, which has only 2 muscles and 2 joints. So it'd take you a really long time for a model like this to just manually adjust the bang-on times of these muscles and the initial poses of these joints to get it to do a squat jump for its true maximum height. So in this study, that's why when you're reading through it, they talk for quite a while about optimization here, optimizing those stimulation signals or optimizing those bang-on times of the muscles to get the model to jump as high as possible. What that's doing is basically an automated way of doing what I described here, of systematically manipulating these variables that influence how high the model jumps. So when they talk here about optimization, they're basically repeatedly solving the equations of this model or repeatedly performing many different simulations of jumping with many different feasible bang-on times for all 6 of these muscles, and doing that in an algorithm in a systematic and automated way to figure out what are the specific bang-on times that get this model to jump as high as possible. Okay. With that, they then wanted to determine whether the simulation that they produced, whether the model that jumped for maximum height was a realistic representation of real human movement. Okay, so they also took some measurements of jumping for maximum height from actual human subjects. Okay, so they went into a gait lab and had them stand on force plates and jump as high as possible, and did some motion capture to measure the motions of the body segments and the joints, and then compared those motions in the human subjects to the motion that the model did when it tried to jump for maximum height, to gain some confidence in if the model was actually performing realistically in comparison to human subjects. Down here in figure 2, you can see at the top the average motion of the human subjects that came into the lab and did the experiment and jumped as high as they could. It says well-trained volleyball players here. I think these might have been the Dutch men's national team. So some pretty skilled, pretty talented and good jumpers here. And on average, they jumped to a peak height of 0.45 meters in their squat jump. And you can see here the kind of sequence of joint motions that those individuals went to on the ground when they were performing the jump. Down here, then, in the next figure, in figure 3, I believe, you can see some examples of the simulated motion of the model. Okay? And so if you just look at the general poses of the joints that the model went through here and compare those to the poses, the kind of the time series of stick figure snapshots of the human jumpers here, they're pretty similar. They're at least qualitatively resembling each other. Well-trained players jumped, or well-trained humans jumped to 0.45 meters, and the model jumped to 0.4 meters, so a little bit lower than the human subjects jumped. But remember, these were very well-trained human subjects, so pretty reasonable result here. Model jumped to at least a qualitatively similar height to the human subjects, and did it with movement that was also roughly similar to the motion that the human subjects did. So just gaining some confidence there that the model here is a realistic representation of actual human jumping. Okay, then what did they do? The purpose of this study was to investigate the importance of muscle strength, or the sensitivity of jumping height to the strength of the muscles in the model. And this is, of course, a common intervention that an athlete might do if they want to jump higher, right? Well, you need to increase the strength of your muscles. So it's a common thing we might assume is necessary for improving jump height. Okay? So what they did here was they took this simulated jump for maximum height, and then they took the model and increased its muscle strength. They did this by increasing the strength of all the muscles in the model, and then they also did it by just only increasing the strength of the knee muscle, the vastus, or the vasti muscle in the model, which is typically considered the most important muscle group, or certainly one of the most important muscle groups for vertical jumping. Okay? And you can see here in table 1 the results of what they did there. On the left is the muscles that were strengthened, either the knee extensors, the quadriceps, or all 6 muscles in the model. And they increased, in each of those conditions, they increased each of them by either 5%, 10%, or 20%. So a 5, 10, or 20% increase in the strength of the knee extensors, and a 5, 10, or 20% increase in the strength of all the muscles in the model. They then show here in the other 2 columns in that table 2 categories of results. It says change in jump height before reoptimization and after reoptimization. What's that reoptimization business? What's that getting at? That is the real core central element of this result, and the really important piece of the result, this before and after optimization or reoptimization. Notice here, just to kind of start hammering it home right away, notice that before reoptimization, which I'll explain what that is in a second, before reoptimization, when you increased the strength of either the knee extensors or all the muscles and increased them by any amount, 5, 10, 20%, didn't matter, the change in jump height was negative. Okay? The model actually jumped lower, in some cases quite a bit lower, like 9 centimeters lower. That's a large decrease in jump height. The model jumped lower. Its performance decreased fairly substantially in some cases by increasing the strength of the muscles in the model. Okay? That's kind of strange, right? Strength's good for jumping, right? Only after doing reoptimization, after increasing the strength of the muscles, were they able to get an increase in jump height, and were they able to get the kind of the expected result that you would see, that the more you increased the strength, if you just look at the knee extensors, the greater the increase in jump height, and the greater increase in jump height you got if you strengthened all of the muscles versus just strengthening the knee extensors. Okay, in some cases, so in strengthening all of the muscles by 20%, they increased jump height by almost 8 centimeters, so almost a 20% increase in jump height, assuming the model started at with a 40 centimeter jump height, like we said earlier. Okay. Now, what is this reoptimization business? Recall that to generate the simulation in the first place, they had to optimize the bang-on times for each of these muscles. Okay, so in my model here, that would be these two values here. Okay, to get the model to jump as high as possible, I fiddle around with those values and figure out, okay, which ones make it jump as high as possible. That's what they were doing here also as well to generate the simulation in the first place. Figure out what are the bang-on times for these muscles, the times during the simulation that they switch from their squat value up to their max value to get the model to jump as high as possible. Here in these two conditions in table 1, before reoptimization means they increased the strength of the muscles, but they did not repeat that optimization process. They just plugged in the same old bang-on times from when the muscles were weaker. Okay? Over here on the right, where it says after reoptimization, that's where they increased the muscle strength, but then also repeated that optimization process. Okay, started from scratch and did the optimization again to find new bang-on times for all the muscles to then maximize jump height. Okay? So, and you can see here in figure 4 an example of the model jumping with the 20% stronger knee extensors without reoptimizing the muscle strength. You can see here it extends its knee way too much, and it doesn't have its trunk pointed up right enough, and it's actually jumping 9 centimeters lower than it did to start with. Whereas if you see here that same model with 20% stronger knee extensors, but with the bang-on times reoptimized, then it jumps has a similar pattern of motion to before, and with that new strength, then jumps about 10% higher. So same model here in figure 1, and or in the top of the figure and the bottom of the figure, but the top or the bottom one jumping 12 centimeters higher than the top one, with the difference being the bottom one reoptimized the bang-on times, and the top one did not reoptimize the bang-on times. It assumed they were the same times from when the model was weaker. Okay. So by increasing the strength, the model was able to jump higher, but not without reoptimizing its control of its muscles. And what is the practical relevance of this for athletes, for individuals training for jump height? Practical take-home message here is that it's not just enough to get stronger. Okay, if all you do is get stronger and you don't practice your jumping, you don't practice your technique, you don't practice your control and learn to take advantage of that new strength, you're not necessarily going to jump higher, and you may actually jump lower. Okay, not from like increase in muscle mass or anything like that, and making it harder to jump because you're heavier. They didn't actually change the mass of the models here. They just changed the strength of the muscles. The decrement in performance there would be because the control is now not tuned to the new strength. Okay, and is that a big deal? Is that a small deal? Well, it seems like here that it's a big deal. It's impairing jump height by quite a bit here, losing 9 centimeters of jump height. To take advantage of that new strength, it's not just enough to get stronger. You also have to practice. You have to learn how to use that new strength. Okay? This ties into one of the all-time greatest interviews with an athlete, and this was Allen Iverson, who I don't think is too long out of the NBA for you guys to not have heard of him. I'm getting a little up here in the years, and sometimes the athletes that I remember aren't athletes that the students in class remember. But this is one of Allen Iverson's interviews. He was always an entertaining fellow at a press conference, along with being one of the best players in the league throughout most of his career, but was always an entertaining fellow in press conferences. This was a press conference he had after a game in the middle of his career, so like in his prime when he was one of the best players in the league, and he was getting asked about how he had missed practice recently and what was going on there, and this was his response.
I mean, listen, we talking about practice, not a game. We talking about practice. not a game, not the game that I go out there and die for and play every game like it's my last. Not the game. We're talking about practice, man. I mean,
so this interview is famous because you can see it's a 2-minute clip, and he says practice something like 30 times in the interview. Just practice, 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 practice. So it sounds like he's saying we don't need to talk about practice. I don't need to practice. I'm best player in the league. Let's just talk about the games. He later on, after he was retired, he's fairly famous for this interview. This is well known and generated a lot of memes and stuff like that. He later on, after his retirement, clarified that he thinks he was misinterpreted here, that he spoke poorly and didn't get his message across. Really, what he was trying to say, or at least what he says he was trying to say, is consistent with the message of this study, that it's not enough just to get stronger, just to be strong. You got to practice. If you increase the capabilities of your body, you got to practice and learn to use those capabilities. Okay? He clarified, and in his clarification, what he said he was really trying to say here is kind of a are you kidding me type of thing. Like, I'm the MVP of the league. I'm one of the best players in the league. Is it possible that I could be that good and not practice or not have to practice? And I can't tell you the exact words that he used. I'd probably get in trouble with the university. But what he said, the edited version of what he said was that it would be a bad somebody who didn't have to practice and could go out and be MVP of the league. And yeah, I'm Allen Iverson, but I'm not that good. I still have to practice. And so he was actually, it sounds like he's not, but he was actually supporting the point that this study is trying to make, that you got to practice. No matter how good you are, no matter how strong you are, you got to practice and learn how to use that strength. Okay? So long story short, if you want to jump, yeah, it's good to be strong. If you want to be lazy in the gym and just want to train one muscle group for jump height, I guess you could train the knee extensors. It's better to train everything, overall body strength for purposes of jump height. But if you want to be lazy and just do one muscle group and jump height is your goal, then knee extensors you could do a lot worse than focusing on knee extensors. But regardless of the strength that you gain and which muscles it is, to take advantage of that, you got to practice. You got to learn how to use the strength. So don't just train for strength if you want to jump high. Train for strength, but also practice to use that strength and work on your technique. Okay, that is it for today.